Welcome to today's Explainer. I want you to imagine the microscopic world for a second. We usually think of it like a static, boring diagram in a textbook, right? Well, actually scratch that. It is a completely bustling, dynamic environment where molecules are literally always on the move. It's this vibrant ecosystem of invisible particles constantly traveling, driven by some pretty fundamental laws of nature. And today, we're going to tell the story of two distinct realms of this great molecule migration: osmosis and diffusion. To kick things off, picture this. You're stuck in a completely packed, super crowded room. You naturally want to spread out to find a bit of breathing room, right? Well, molecules do the exact same thing. But why do they love to travel so much? It all boils down to what scientists call the kinetic energy of random motion. Because of this energy, molecules are constantly bumping around, colliding with each other, and they naturally just want to spread out from where it's tightly packed to where there's a bit more space.
Chapter 1, the crowded molecule room. So our first foundational process here, the rule governing so much of how cells interact with their world, is diffusion. Because of that kinetic energy we just talked about, molecules naturally intermingle. The absolutely crucial point to remember is this: molecules will always journey from an area of high concentration, the crowded party, to an area of lower concentration. And they'll keep on moving, over time until they are equally spread out everywhere. Total balance. Let's break down how this actually works when a cell gets involved. If you've got a super high concentration of molecules just sitting right outside a cell, then naturally, more molecules are going to enter the cell than leave it. Conversely, if it is super crowded inside the cell, more molecules will escape to the outside. It's just a continuous, natural drive toward finding equilibrium. Chapter 2, Water's Magic Gate. Now, while we've been talking about particles in general so far, water is a little different. It has its own highly specialized type of movement called osmosis. You can kind of think of a partially permeable membrane as a magic gate surrounding the cell. Osmosis is basically just a special case of diffusion, but the big twist here is that the concentration of solutes, those hidden substances dissolved in the water, heavily influence how and where the water travels through that gate. Chapter 3, the plant cell story. When our first character, the mighty plant cell, reacts to water, it actually changes its internal shape. But surrounding it is this incredibly strong, unyielding cell wall. Because of this protective boundary, the plant cell is kept completely safe from bursting open. It allows the cell to withstand immense pressure when water rushes inside, pushing the cell's contents right up against that sturdy wall. Let's map out this epic three-part journey for the plant cell. First up, when you put it in a solution with a higher water potential, meaning there's way more free water outside the cell, water diffuses inward. The contents expand against the wall, reaching a firm state we call turgid. But if the cell is placed in a solution of lower water potential, the water diffuses out. The cytoplasm shrinks, and the cell gets soft, or flaccid. Finally, in extreme conditions where too much water leaves, the cytoplasm completely pulls away from the cell wall, becoming what we call plasmolyzed. Chapter 4, the animal cell story. Now we meet our second character, the animal cell. And unlike our sturdy plant cell, the animal cell is vulnerable. It's journeying through this microscopic realm completely without the protection of a tough outer wall. This lack of a rigid barrier perfectly contrasts the animal cell's fate with the plant cells. It leads to a daring adventure with some pretty dramatic and honestly dangerous consequences when a cell lacks that armor. Without that cell wall, things get wild. If an animal cell is placed in a solution with a higher water potential, water rushes in. The cell expands, but with nothing to hold it back, it swells way too much, literally bursts open, and becomes hemolyzed. No way back from that. On the flip side, if water rapidly leaves the animal cell by osmosis, the whole thing shrinks down, looking all shriveled and wrinkled. In this state, it is crenated. Chapter 5, Two Microscopic Tales. Let's put these two rules side by side to really lock this in. On one side, we have diffusion. This is for your particles, like ions and molecules, seeking balance by moving from an area of higher concentration to an area of lower concentration. On the other side, we have osmosis. This is water's specific, highly specialized journey across a selectively permeable gate. And notice that water moves from a hypotonic solution, where there are fewer solutes, into a hypertonic solution, where those solutes are highly concentrated. So, the takeaway here is that while both of these processes are desperately seeking balance, the rules of their travel are totally unique. I want to leave you with a final thought today. Next time you're at home watering a drooping, flaccid houseplant, and you watch its leaves slowly perk back up,
Which epic, microscopic journey are you actually helping begin? Think about that invisible physics happening right in front of you. Thanks for joining me on this explainer, and keep exploring.